All right, guys, just talking through the Unit 10 energy review here. I've filled in a lot of this already, and I'll just talk through it just to save us time and energy. I will go through the process of calculating all the math problems, though, so you'll be able to see all of that, even if I've laid some of the pieces out already. So, this unit, we worked on energy. So we had 4 equations. We had one was for work, which is force times distance, F times d, which is measured in joules. Another way you could represent work, if I lift an object straight up, the force is actually equal to its mass times gravity, so m times g times d. And if you look really closely, that's actually the same as basically lifting an object straight up for potential energy. So those two equations are exactly the same. The equation for power is work divided by time. It's measured in watts. And since it's work, it's also force times distance divided by time. Potential energy is mass times gravity times height, measured in joules for potential and kinetic. Kinetic is 1/2 times mass times velocity squared. So how do we get energy? We eat, and we see the food energy label is calories on labels, not joules listed. There is obviously a relationship between calories and joules, but we don't necessarily have to know that, but just realize that that is basically energy, is calories. So an energy that is stored is potential, motion is kinetic. When we put energy into something, our body is where that energy is coming from. Because the law of conservation of energy, you can't just create energy, that has to come from somewhere. So number 10 here, in order to do work, we have to apply force, and the object has to move over a distance, right? That's what work means, force over distance. So I could apply a huge force against this wall, but if it doesn't move, my distance is 0, so there's no work. And that's the main idea here. Now, the next set of problems are all about relating mass to properties of energy that we're talking about this unit. So we have 2 people, Big Billy, we're assuming his mass is greater than little Sarah. Okay, so we're just assuming one has high mass, one has low mass. They both climb a ladder to the same height. Which one has more potential energy? Because potential energy is mass times gravity times height. If they're the same height, gravity is the same. Higher mass, Big Billy, means higher potential energy. So which one did more work? Same thing. Work is force times distance. The distance is the same, but since mass is higher, means more force. Higher force means higher work. If they did it in the same amount of time, power is work divided by time. So the one with the higher work, Billy, had higher power. And that means if Sarah wanted to have the same power output, she would have to do it faster to make her power go up. So this one, same velocity, who has more kinetic energy? Again, kinetic energy is 1/2 times mass times velocity squared. If their velocity is the same, higher mass Billy means higher kinetic energy. For little Sarah to have the same kinetic energy, she's going to have to run faster. Okay, because her mass is lower, her velocity has to be higher to match kinetic energy. Stacking wood, to increase power, I have to do it fast. Okay, so this is just some conceptual pieces to our equations. So we always find the biggest hill on a roller coaster at the beginning. Why? Because we're going to add a ton of potential energy at the beginning so that the kinetic energy will have enough to finish the ride. And obviously we're transferring a lot of that energy, that potential, to kinetic. But in that case, we also have friction, air resistance, a lot of pieces like that that are ultimately going to transfer some of that potential energy out. So energy can never be just created. And that's why at the beginning of a roller coaster, you have the mechanical aspect that raises you higher. So you raise a book and you drop it. Just before it hits the floor, what kind of energy is that? Kinetic, because it's moving. If work is done by you, I'm losing energy, I'm expending energy. If it's done to me, I'm gaining energy. Work to lift is equal to the potential energy of an object. If you put rock on a shelf, you're increasing its potential energy. And this number 22, that's because, remember, those two equations, PE, mgh, and work is equal to force times distance, or mass times acceleration times distance. That's why. Two different people walk up a set of stairs. Do they both do the same work? Only if they have the same mass. Otherwise, their work will be different. We've seen this diagram before. High potential, high kinetic, sum of both. No velocity, high velocity. Now we're getting to the math problem, so I'll spend a little bit more time here. So what I did is I took the equations, potential energy, determined potential energy, which is mass times gravity times height. I laid out the mass, gravity, and height constant. And now I'm just going to plug them in. So the mass is equal to the 10 kilograms times my gravity, which is 9.8 meters per second squared, times, I'm just going to 1.5 meters. I multiply all of them together, and I'm going to get, and give me a second to calculate, 10 times 9.8 times 1.5 gives me 147 joules of potential energy. Okay, here I got kinetic energy, I got mass and a velocity. So when I'm plugging this in, I'm going to get 1/2 times mv squared. Now here is 1/2, and then plug in my mass, times my mass, which is 10 kilograms, that's 19, times, and then here's the big idea, is whatever my velocity is, in this case 4.5, I have to plug that in first to my calculator. Okay, so what I end up getting here is 4.5 squared. 4.5 times 4.5 gives me 20.25 times 10 times 1/2, 4.5, is equal to 101.25 joules of energy. Okay, that's the same idea here, so I'm just going to copy and paste this one from here to here and adjust what I need to. How much kinetic energy does a car have if its mass is 2,000 kilograms and it's moving at 25 meters per second? 25 times 25 gives me 625 times 2,000 times 1/2 gives me 625,000 joules of energy. Okay, I got another mgh one here. So I'm just going to copy and paste the work from here. Calculating potential energy. The only thing that's different in this case is the mass, which is 3.5 kilograms. Acceleration due to gravity is the same. The height is 2.4 meters. How much potential energy does it have? 3.5 times 9.8 times 2.4 gives me 82.32 joules of energy. Okay. Now we're moving on to work, which is force times distance. So force is 300 newtons times a distance of 30 meters is equal to 9,000 joules of energy. Same thing down here, different work because I got a different force and a different distance is equal to 250 times 14, which is equal to 3,500 joules of energy. So a lot of times the hardest part is picking out what you have. So I have newtons, that's force. I have distance, 0.8. How much work does he do in one stroke? So here I just take 250 times 0.800 meters is equal to 250 times 0.8. This is equal to 200 joules of work. This is one stroke. So I got to multiply that by 50 to give me 50 strokes, which is 10,000 joules of work in 50 strokes. Okay. Now we're getting into some fun stuff. So remember, work is equal to force times distance. And since force is equal to mass times acceleration, A is equal to acceleration due to gravity here because it's going straight up and down. This is my equation that I'm getting, mass times gravity times distance. So my mass is 95 kilograms times gravity, 9.8 meters per second squared, times a distance is 0.90 meters. It's going to give me an answer of, I'm going to put units on this quick, 95 times 9.8 times 0.9 is going to give me 837.9 work joules of work. Okay. 34 is probably the hardest problem on the review because I have a lamp sitting on the table with a height of 1.5 meters, mass of 2.2 kilograms. It bumped, falls off the table. How fast is it going before it hits the floor? Okay, so remember, law of conservation of mass, all the potential energy it starts with, which is equal to mass times gravity times height, which is equal to 2.2 times 9.8 times 1.5 is equal to 32.34 joules of energy. Now, all that potential energy it starts with is also equal to how much kinetic energy it has at the bottom. So 32.34 joules is how much kinetic energy it has. Its mass is still 2.2 kilograms. So then my velocity is what I'm solving for here. Okay, so that now I just got to plug things in the way that I normally would. Okay, so KE is equal to 1/2 v squared. So I'm just going to mirror this here. I get 32.34 is equal to, that's not equals, is equal to 1/2 times mass, which is 2.2 kilograms, times velocity squared. Okay, so then this is going to be 1.1. Okay, so I'm going to have 32.34 and divide that by 3 or 1.11. 1.1 is equal to v squared. So then I got to take the square root of this. So give me 2 seconds. I had to kind of go find a square root symbol I could do here. So when I multiply these two, I get 1.1. So it's 1.1 times v squared is equal to 32.34. So to get v by itself, I have to divide both sides by 1.1. That gave me 29.4. So 29.4 is equal to, and I guess I should probably do it this way. So 29.4 is equal to v squared. So I got to take the square root of both sides to get v. And when I do that, square root of 29.4, give me 2 seconds on my calculator, I end up getting 5.4 meters per second. And then that would be my final answer here. So it's a tough question. There's a lot going on there. I'm just going to change the text size here quick. And okay, here we go. So now we got power, which is just work divided by time. So here I got work 3960 joules of work divided by a time of 50.0 seconds is equal to 3960 divided by 50, 79.2, and it's watts, which is a W, but technically it's like an italicized W. So that would be watts here. So here I got same type of problem. The reason why it's italicized because notice work is a W as well. So I get 400 joules of work being done in a time of 4 seconds, which should give me an answer of 100 watts of power. Okay. Lastly, we got 2 problems here. So 37 we got, and 38 we got 2 pie eaters. we got 10 newtons of force being done over a distance of 0.2